The next topic is Polarization, chapter 5.3.5. By the end of this section, you should be able to understand what is meant by plane polarization. Describe how polarization can be used with models to investigate stresses in structures. So, plane polarization. Let's have a look at this diagram to help you understand this. Now, for example, if we have this vibrations in all directions, then we pass it through this. So imagine that there is a slit here in the shape of this arrow. So what will happen? Only this vibration or oscillation can pass through this. So that is a polarizer, because here we have the oscillations in all directions. Once it passes through the polarizer, it will only be in this direction. So you see that. Now again, if we have the polarizer which is allowing vertical vibrations, again it can pass through that. So still we have the same as before. Now if we let it pass through, if we try to make it pass through this, here it's allowing only the horizontal vibrations. So once it passes through that, there will be no vibrations. Okay, no vibrations. So these are polarizers. And if we scroll down, we can see the different topics here under polarization. Polarization by reflection and refraction, polarizing filters, that's what we saw just now, plane polarization, polarization by chemical solution. So there are several ways to cause polarization. And polarization by reflection and refraction, I read that already. So here is the definition, key definition. What is polarization? Polarization refers to the orientation of the plane of oscillation of a transverse wave. If the wave is plane polarized, all its oscillations occur in one single plane. So polarization refers to the orientation of the plane of oscillation of a transverse wave. If the wave is plane polarized, all its oscillations occur in one single plane. Now that's what happened here. Here it's plane polarized. Now all its oscillations are in one, we can say in one single plane. But remember, even here it's also, now if it's not going, if imagine there is a surface here, a plane. A plane is an imaginary surface. So if all these oscillations are in the same plane, it's already plane polarized. But let's say these are in different planes, and this will allow only oscillations in the vertical plane and also only this oscillation. So here we can say it's polarized in addition to being plane polarized. So Polaroid filters transmit light waves if their plane of polarization matches with the orientation of the filter. So here, in addition to the plane of polarization, the plane of polarization must match the orientation of the filter. So here the orientation is an arrow shape in the vertical direction. So it will only allow those, actually this is not an arrow, this is referring to the oscillation. Okay, so it will only allow oscillations in the vertical direction, and that also in the vertical plane only. Plane polarization. Transverse waves have oscillations at right angles to the direction of motion. So, transverse waves, for example, electromagnetic wave is a transverse wave. And in the case of electromagnetic waves, we have electric fields and magnetic fields vibrating perpendicular to each other like this. So for example, you see here in red, that is one plane of oscillation. In blue, it's another plane of oscillation. So these two are perpendicular to each other. So this can be the magnetic field, this can be the electric field, and they are perpendicular to each other. Transverse waves have oscillations at right angles to direction of motion. You know, when you learned transverse wave, you learned this already. Remember, we learned about transverse waves and longitudinal waves, and you have to know the difference between these two. Okay, in transverse waves, the oscillations are perpendicular or at right angles or normal to the direction of motion. In many cases, the plane of these oscillations might be in one fixed orientation. Figure A shows the electric red and magnetic blue fields in an electromagnetic wave. So that's what they are referring to here. In this example of, say, a light wave, the electric fields only oscillate in the vertical plane. You can see it's shown in red. The wave is said to be plane polarized, or more precisely, vertically plane polarized. Now we learned what is polarization. Okay, if you go back to the definition in the last page of this subchapter, polarization refers to the orientation of the plane of oscillation of a transverse wave. If the wave is plane polarized, all its oscillations occur in one single plane. So make sure you understand this definition. Alright, so let's see, go back up. Polarization is only possible with transverse waves. If a wave is polarized, it must be a transverse wave. So this doesn't work with longitudinal waves. You have to keep this in mind. Polarization can occur only with transverse waves. A polarized electromagnetic wave. Now why? Because we have only the vertical and the horizontal oscillations. Often many waves travel together with oscillations in a variety of planes. In this case, light from this source is said to be unpolarized. This is how light emerges from a light bulb, a candle, and the sun. So this is already plane polarized in the vertical plane and the horizontal plane. The wave is said to be plane polarized, or more precisely, vertically plane polarized. For electromagnetic waves, the plane of the electric field's oscillations is the one that defines its plane of polarization. Next one, polarizing filters. Unpolarized radiation can be passed through a filter that will transmit only those waves that are polarized in a particular plane. See, you can see that here. Waves on a string could be polarized simply by passing the string through a card with a slit in it, which will then only allow oscillations to pass through if they are in line with the slit. Yes, so you can think of this, for example, a rope. Even there are diagrams in the other books I can show you where they show this polarization of different waves. For example, even waves in a rope. For light waves, the polarizer is a piece of plastic impregnated with chemicals with long chain molecules called a Polaroid sheet. The Polaroid filters will only allow light waves to pass if their electric field oscillations are oriented in one direction. Polaroid filters transmit light waves if their plane of polarization matches with the orientation of the filter. Figure B illustrates the effect of Polaroid filter. So this is a Polaroid filter, this is a Polaroid filter, this is also a Polaroid filter, also called polarizers. So remember this here, Polaroid filters on light from a bulb. So this is a light source, and it can, in this case, is a bulb, they tell you, that will have oscillations in all directions. It starts unpolarized, so that light is unpolarized with vibrations in all directions, as you can see here. Here it shows as if it's in one plane, but it's in all directions. The first filter only permits vertical vibrations. So you see all these horizontal and other vibrations are not passing through this Polaroid filter or polarizer. It only allows vibrations in the vertical direction, which can pass through this. So it's a Polaroid filter, and the light is transmitted vertically plane polarized. So again, the first filter only permits vertical vibrations, so they are selected and light is transmitted vertically plane polarized. So only those in the vertical direction can pass through. The first filter only permits vertical. Okay. The second filter is oriented in the same vertical direction and the light will pass through this without change. So again, same as before. You can see this and this. You can say they are identical. So this is already plane polarized and this allows that same vertical oscillation to pass through. The third Polaroid filter is oriented horizontally. You can see that here. This blocks vertically polarized light and so no waves are transmitted beyond it. So this blocks vertically polarized light and so no waves are transmitted beyond it. Vertically, yes. The second and third filters are referred to as crossed Polaroids, as their orientations are at right angles and together they will always block all light. So this allows only in the vertical direction, this allows only in the horizontal direction. So eventually it will prevent all the vibrations passing through this filter. That's why it's called crossed Polaroids, because these orientations are perpendicular to each other. This is vertical, this is horizontal, though that will prevent or block all the light. So you can try this with maybe the Polaroid sunglasses. You can take two of those glasses and orient them perpendicular to each other and you will see you can't see through them in that case. Investigating structural stress. We can use crossed Polaroids to observe stress concentrations in clear plastic samples. Stress analysis using crossed Polaroids. The first Polaroid produces polarized light, which passes into the plastic sample. Stressed areas have their molecules in slightly different orientations, and this will affect the passage of the light through the plastic. This effect varies with color of the light. When the second Polaroid acts on the emerging light, some of the light will have traveled slightly more slowly through the plastic and will destructively interfere with other light waves of the same color. Thus, depending on the degree of stress in the plastic, the colors that emerge will vary. Differently stressed areas appear as different colors through the second Polaroid. Changing the stress on the plastic will alter the internal stress and the interference pattern will change. Engineers use this to see stress concentrations in models of structures and to observe how the stress concentrations change when the amount of stress changes. This allows them to alter the design to strengthen a structure in regions of highest stress. Engineering stress analysis using crossed Polaroids. I think it's self-explanatory. If you still didn't understand this, go through this again. I think you should understand it. It's very simple. It's only like one paragraph. Okay, we will go to the next topic, polarization by reflection and refraction. When unpolarized light reflects from a surface, so here you can see, for example, here you have oscillations in the vertical and the horizontal direction. Once it gets reflected, the oscillations are only in the horizontal direction. When polarized light reflects from a surface such as a road, the waves will become polarized. The degree of polarization depends on the angle of incidence, but is always tending towards horizontal plane polarization, as shown in figure E. So that is also, I think, explanatory, self-explanatory. I already anyway explained it. So we have unpolarized light reflecting from a surface. For example, this can be a road. And when it gets reflected, the waves become polarized. The degree of polarization depends on the angle of incidence. Remember, the angle of incidence is the angle between the incident ray and the normal. So if you draw a normal is a line perpendicular to the surface, and the angle of incidence is the angle between the incident ray, which is this, and the normal. So the degree of polarization depends on the angle of incidence, but is always tending towards horizontal plane polarization as shown in figure E. Reflection can polarize waves. Okay, so you see here what happens. Light waves incident on a surface into which they can refract. See figure 5.3.1. Sorry, see section 5.3.1. Such as a pond. So you can refer to that section for more information. We are in the last part of this topic. So then we have the next topic, which is another different topic. So if you go back to the beginning of this, okay, I have already uploaded the explanation videos for these chapters that they are referring to. You can go through them and understand. Refraction can polarize waves. So here you have refraction that polarizes, reflection also polarizes. So this is the unpolarized light. In air, when it goes to glass, partially polarized light, perpendicular to plane of paper. Light waves incident on a surface into which they can refract. See section 5.3.1. Such as a pond will reflect partially horizontally polarized light, as in figure E. So this is that. But will also transmit partially vertically plane polarized light into the medium, as in figure F. See, so both of these happen. So reflection, partially plane polarized, and here we have transmission or refraction. So there also we have partially vertically a polarized light here. So unpolarized, partially polarized light perpendicular to the plane of paper, partially polarized light. Reflection can polarize waves. So reflection can, and also refraction can polarize waves. Okay, so the next topic, polarization by chemical solutions. See here we have a sugar solution. Sugar solutions can rotate the plane of polarization. The degree of polarization on a particular wavelength. You know, wavelengths can correspond to colors. You know, we have the colors of the rainbow from the longest to the shortest. You have learned the acronym ROYGBIV: red, orange, yellow, green, blue, indigo, violet. So they have a certain range of wavelengths for those particular colors. The degree of polarization on a particular wavelength or color depends on the concentration of the solution and how far the light has had to pass through it. This gives rise to the changing color seen along the length of this tube of sugar solution. So I think you understand why the color changes along the length of this tube of sugar solution. We have sugar solution in here. So this is an example of polarization by chemical solutions. The analysis of stress concentrations investigated above works because different parts of the plastic model, that is this one, okay, we are referring to this one. The analysis of stress concentrations investigated above works because different parts of the plastic model have different effects on polarized light. This is also the case with some chemicals such as sugar solution. The amount of the concentration of the sugar solution varies the angle to which it rotates the polarization of the light. So again, the amount of the concentration of the sugar solution varies the angle to which it rotates the polarization of the light. So again, very simply, depending on the concentration of the sugar solution, the angle to which it rotates the polarization of the light can vary. We can use Polaroid filters to analyze strength of the sugar solution by measuring the angle at which the light polarization emerges after passing through the solution. So this is a way we can find the strength of the sugar solution. Alright, so that we have come towards the end of this subchapter on polarization now. Again, very simple. If you still have more questions, I recommend you to just read that particular part. You should get it. So basically, this is what we have. We have the Polaroid filters or the polarizers, which makes the oscillations happen in one plane. And we saw this electromagnetic wave, a polarized electromagnetic wave, because we have oscillations in let's say in the vertical plane, and we don't have oscillations in all different planes. So that's why it's polarized. The wave is said to be plane polarized, or more precisely vertically plane polarized. For electromagnetic waves, the plane of the electric field's oscillations is the one that defines its plane of polarization. Then here we have the example we went through, investigating structural stress, so using another use of these polaroids, crossed polaroids especially. We can use them to observe stress concentrations in clear plastic samples, and I went through this. You can go through that. I think it's self-explanatory, as I said before. Okay, so you have polarization by reflection and also by refraction. Then polarization by chemical solutions. So by measuring the angle at which the light polarization emerges after passing through the solution using Polaroid filters, we can analyze the strength of the sugar solution. Okay, make sure you answer all these questions, and we have come to the end of that chapter. Therefore, make sure you answer all these exam style questions also. After you answer each question, check the answers for all those questions, so that you know you have done it correctly. Otherwise, if you go to another question without checking the answer to the previous question, that next question may be similar to the previous question, and you might make the same mistake in the next question. So always, after you finish one question, check the answer before you start on the next question. So that's the end of that, and we can discuss another topic in another video.